there's more questions. So hi everybody, like you said, I'm Kieran, I'm from the University of British Columbia, and today I'll be talking about a sort of dive that I did a while back into the effect of curvature on soft 3-axis force sensors. My research focuses on the 3-axis force sensors, and the effect of the different factors in soft sensing, such as curvature or strain or other forms of deformation, is vital to understanding how they work. So, to kind of situate the work that I am doing here, and why we're looking at curvature, I'm highlighting two specific applications. The first is very common in soft sensors, or both these are very common for soft sensors. The first is the focus of my actual research, which is prosthetics, specifically upper limb prosthetics. And the second is an application that is fairly common in other researchers in our lab, which is wearable technologies. And you can imagine, especially looking at wearable technologies for the arms and hands and upper limb prosthetics, there are a lot of curvatures. We're basically made out of a whole collection of curvatures. And not only that, but a lot of different curvatures. Applying a sensor to the fingers versus applying a sensor to the arms, all of it has a very varied effect on how the sensors will function. And just to situate my work in terms of other work that's going on, because soft sensors, especially soft 3-axis force sensors, are kind of a hot topic right now, I have grabbed 3 examples. These are just the first ones that came to my head. Of course, there's tons of research going on in this field right now. The first is Guo et al., who are doing, I believe this is textile-based force sensors, and they're looking at applications like the one shown here, where they're applying it to a insole that would be worn, and the curvatures are very large there, but it involves higher forces. There's also Ham et al., who have a sensor that's relatively similar to the one I'm talking about today. They are looking at, in this paper that I got from, they are looking at soft grippers, which have curvatures closer to the finger, which will be a lot harsher. And then there's Bouchy et al., which is a bit of an older paper, but they have a very skin-like sensor, which ties a lot into the prosthetic applications that I look at, and the whole e-skin factor of the soft force sensing. And as a final plug for my work specifically, the whole motivation for the work and a large part of how I've been able to do this work has been our close collaboration with Honda Japan for the last few years. We actually have our collaboration member in the audience right now, and he'll be presenting later this week, although I don't remember exactly which day. And to tie it into more of the upper limb force, soft 3-axis force sensing, we've been looking at applying the sensors to a humanoid robot, which would be used for teleoperation. So you can see these aren't the sensors I'll be talking about today in specific because they are newer. This work was done a little while ago that I'm talking about today. But the sensors are applied to a variety of different curvatures, namely the curvature of the finger here and the slight curvature of the palm. So thank you, Mr. Ishizaki, for your correspondence and your support of my research. And in case they're very common at this point, I think, or relatively common, but in case people aren't familiar with the concept of capacitive force sensing, the basis of the sensor is that the sensor that I'm looking at today is 3 conductive elements with a structured dielectric layer. In this case, we have a shielding electrode. The sensors are capacitive, like mentioned in the title. If you've worked with capacitive sensors ever, you know that they are a nightmare if you don't have proper shielding, because if something moves near it, if you approach it, if you even think about the sensor too hard, you tend to get increased noise or signal jumps. So we always include shields in all of our sensors. And then the rest of it is just a relatively simple parallel plate electrode structure that forms a capacitor. One of the big things that we do a little bit differently from other sensors in the field where there are porous dielectrics or solid dielectrics, we actually take a different approach and macrostructure dielectrics. So it's not really visible here, but we have, this is not to scale, but there are 3 large pillars, and in between there will be air. And the reason why we do this is to increase the sensitivity of the device. By introducing air instead of elastomer, we get more deformation for the amount of force. The capacitance change that we're reading is directly related to the deformation, so we get higher sensitivity. And we've also found that by doing macro structures instead of relying on microstructures or porous materials or solids, we heavily reduce the hyperelastic material properties that you often see in the soft materials used here. So Here's the actual sensor architecture I'm going to be talking about today. We have a top view and a side view. And in order to do the 3-axis part of the 3-axis force sensing, we require 5 electrodes. And the way that we separate normal and shear force with this 5-electrode structure is by simultaneously looking at the overall change in capacitance and the differential change in capacitance between paired electrodes. So you can see in the cross section here, I've chosen C2 and C4 and have a little animation, but basically on the application of pressure, like this, we see all 4 of the electrodes will get closer to one another, get closer to the base electrode. This causes an overall increase in capacitance in all 4 electrodes. By applying the normal strain signal equation that I show up above, we can get a very mappable normal force signal. Alternatively, if we don't apply normal force and we apply shear force instead, we see that based on the geometry, the non-inline plates C1 and C3 will not move in a way that changes their capacitance relative to the bottom electrode. But we see that C2 will move so there is less plate overlap, and C4 will move so there is more plate overlap. This causes a differential shift in the capacitance. C2 will drop, C4 will increase, and we can apply the equation shown to very precisely extract the shear signal. And I don't think, actually, I apologize in advance, I don't show the data here, but this produces a very recognizable and distinguishable normal and shear signal. We've shown that in some of our previous work. And here I'm just showing in the opposite direction, we get the opposite effect. And to prove that I'm actually doing this, here's an example of the sensor that we used in this research. So ignore the force sensing ring. As I mentioned, we are powered by an industry collaboration, which is very important, but also has external pressures to add more sensing elements than we talk about in this study. So we're only really focusing on this black square in the middle, which is the single electrode of the structure that I just showed. And on the PCB, we have the 4 other electrodes. The reason why we use a PCB for this work, which does make the sensor not stretchable, is because we're really focusing on the application for the fingertip, where we don't need the stretchability, and using a PCB makes the overall system a lot more stable. We're using, in this case, metallic crimps to connect to the soft material. This allows for us to keep the sensor area very soft while still making connection to the PCB. And the materials you're seeing here are Ecoflex 30. It's a silicon elastomer that's very commonly used in sensors. And the black material is just a carbon black, carbon nanofiber silicon elastomer blend that is reasonably conductive. We use capacitive sensors, so as long as we keep the resistance below threshold, we don't notice how resistive the material is. And I don't show it here, but the readout circuit is attached using an FFC cable, and we're using the Cypress PSOC family of microcontrollers due to their onboard capacitive sensing capabilities to measure the capacitance as you see here. So what we did with these sensors is they are very flexible. So we used a customized 3-axis force testing setup using an ATI load cell as a calibration tool. And we'll look at curvatures from 100 to 10 millimeters. These were identified as sort of the range of curvatures we would see from, say, a forearm or a shoulder, all the way down to the fingertip, which would be the highest curvature that we expect. So for normal force, we see that 80 isn't a good representation, but as we increase the curvature of the sensor, we see a dramatic shift in the peak signal for force. I do have to caveat that this is displacement controlled, so you'd see some shift in the peak force. This is because of our setup. Our setup is highly customized, but it doesn't do force controlled feedback. But we see that overall there is a shift in the peak signal that we see for a given force, and the trend is for the sensor to become more sensitive with increased curvature. So, and our peak sensitivity is 0.12% per Newton at 10 millimeters. This is percent is in delta C over C naught, normalized capacitance. And similarly, we see these are the shear sensing signals. What we're looking at here is the calculated differential shear using the equations that I showed before. And we are starting at 0, and we are applying a displacement in either direction, and then measuring the resultant force and looking at the calculated signal as a response. And we see that going up to, these are all displacement controlled, but it all goes up to about 0.5 to 1 Newton of maximum force. we see that there is a similar shift to the normal force where the sensor, as it is curved, tends to become more sensitive in both directions, as shown by the slope of this line. So we see that the peak signal at a given force increases again. Another notable thing that we see in shear that we didn't see as much in force is that the signals also remain highly linear when we increase the curvature, which is very important because of the hyperelastic nature of the materials that we use. It's important that the sensor remains predictable as we increase the curvature. It's vital in terms of the sensor actually functioning on curvatures. And just to demonstrate, we have an example of, so in this slide, I showed just the X direction and Y direction. So this indicates that we are shearing along the X direction taxels here and the Y direction taxels here. I'm not showing the non-inline taxels, but if we look here, we can see another important factor in the sensor maintaining function on curvature, which is a clear separation between the inline and out-of-line taxels. So we see this is the exact same data sets as the previous slide, but I've added in the out-of-plane electrodes. And we see that there's a little bit of a shift in the X direction shear and not so much of a shift in the Y direction, but overall the separation remains very good. Also vital in terms of the sensor actually functioning. If they started muddying together as you introduce curvature, not so good for the collaboration. So overall, we came to a few different conclusions based on our exploration of curvature and sensor response. We see an increased sensitivity to both normal and shear forces. We do see a high linearity in shear forces. Unfortunately, it's relegated to future work, but the normal force linearity was not so fortunate. And we see a overall structural change in the sensor that changes the feel and we use to explain some of the effects that we're seeing. The primary structural changes that we see is as you bend the sensor, we're seeing both a preloading effect on the sensor structure, where the pillars are compressed due to lateral strain on the upper surface, and a thinning of the upper surface due to the lateral strain. There is, of course, also a decreased effective contact area of the indenter that we're using in our setup, which also contributes and would contribute in a practical setting. So our takeaways for this in terms of soft sensor design, the main takeaway that we found is you have to be very careful about how you design the sensors and pay a lot of mind to the expected radius of curvature. So keep in mind the design for a fingertip versus an arm. And what we found was kind of the magic number was keeping the radius of the curvature to width of the sensor elements ratio of less than 1. This is because in the 30 to 10 millimeter jump, we saw a much larger change in sensor function than all of the other curvature jumps combined. This is close to the sensor dimensions. So we're seeing a greatly increased effect on the sensor function as we get kind of close to the sensor dimensions in terms of curvature, which is not surprising, but it's a good thing to keep in mind for design. And just to throw in an application, because we all like applying our work to an actual usable thing, this is discussed a little bit in the paper, but we attached the sensors to a open source robotic hand that we got off of online. And we are able to use the 3-axis force sensor and consideration of the curvature that it's placed on to do different analysis of slip, surface texture, grip force, and mass estimation. So we're actually able to pick up different items and estimate the mass and determine whether they're from shear and from normal force combined, accurately determine whether there is slippage occurring. And I'm almost at time. I'm on yellow light, so I'll very quickly highlight a few other projects going on in the lab that are soft force or soft robotic related. We have some polymer actuators on the far side that are being used for soft feedback primarily. Similarly, we have some nylon actuators that are being used for soft feedback. And we also have a force sensing smart sheet, which is being used for primarily ulcer detection, but it's also moving into some wearables and robotics sections. Good. That's all for me. Just about 15 minutes. So.